Hi, I'm Mason Peterson from the Aerospace Controls Lab at MIT, and I'm going to be talking about our IROS paper, MOTLEE, Distributed Mobile Multi-Object Tracking with Localization Error Elimination. Understanding the dynamic objects in an environment is a critical piece of many robotic systems, like autonomous cars, delivery robots, and robotic surveillance systems. Performing collaborative multi-object tracking with a team can result in a more accurate understanding of dynamic elements, by adding sensor redundancy and by overcoming problems of occlusion by allowing a team to detect moving objects from multiple vantage points. A primary challenge in collaborative MOT is performing data association, determining whether the object that one robot sees is the same object another robot is seeing. Often the most descriptive indicator that two robots are detecting the same object is that the object is detected in the same location by both robots. The images on the right are taken from two different robots, and the green lines indicate selected associations. It is possible for these robots to make these correct associations because the robots' measurements of pedestrian locations were nearby each other as seen on the left. However, to associate object measurements, robots must understand each other's relative poses so that these measurements can be properly transformed into each other's local frames. When robot localization is poor, for instance when localization is affected by drift, then the information about perceived objects' locations is corrupted, as is their ability to perform data association with neighboring robots. This can result in both believing that dynamic objects are in wrong locations and that there are more objects than actually exist, which can further cause undesirable consequences like collisions or over-conservative behavior later on in an autonomy pipeline. Our work, MOTLEE, provides a solution to performing multiple object tracking in realistic scenarios with imperfect localization, enabling distributed mobile MOT. Frame drift is corrected between neighboring robots in a distributed way and in real time by aligning maps of recently observed static landmarks and detections of tracked dynamic objects. We leverage the common consensus filter as has been done in prior distributed MOT works. Each robot maintains a local copy of a tracked object state. When that robot detects a dynamic object, the measurement is associated with one of the local states using a global nearest neighbor approach. The new measurement and covariance information is shared with neighboring robots, and in this way robots reach a consensus on each of the tracked object state estimates. While this is an effective mechanism for performing collaborative MOT, it relies on the assumption of known camera poses. Here, we show qualitative results of a hardware experiment with 3 mobile robots tracking 4 people using RealSense camera images for object detection. Additionally, the T265 tracking camera's visual inertial odometry is used for ego pose estimation. Ground truth and estimated robot poses, as well as ground truth and tracked pedestrian positions, are visualized above. On the left, we see that without MOTLEE, robot frames are misaligned, which leads to incorrect data associations and estimation errors. We will show that by using MOTLEE, we correct for localization drift between robots by performing pairwise frame alignment. Frames are aligned at a regular rate by associating and aligning landmarks and dynamic objects observed in robots' own frames. Each robot builds up a map of locally detected landmarks and then uses the iterative closest point method to associate common landmarks between robots. Once associations between landmarks have been made, landmark pairs are weighted to prioritize the information from pairs of landmarks that were both seen recently and thus represent the current state estimate of the robot. In cases where pairs of robots have many common detections of the same dynamic objects, those measurements have already been associated together and these can be used to perform frame alignment. Additionally, we incorporate the uncertainty associated with frame misalignment, localization uncertainty, and measurement error into the covariances of shared measurements. This avoids overconfidence in any robot's measurements with large localization or frame alignment uncertainties. By performing real-time frame alignment, MOTLEE is able to accurately estimate relative poses of robots and understand the different sources of compounding uncertainty. This in turn allows a team of robots to accurately track the pedestrians, even in the presence of localization drift. Here we show results from this hardware experiment when ground truth localization is used versus when drifty odometry is used with and without MOTLEE. The bottom 2 plots show drift accumulating in the navy line where MOTLEE is not used, and the top plot shows the effects of localization errors on multiple object tracking accuracy. As drift accumulates in the navy line, tracking accuracy significantly degrades. In green, we show that the robots using MOTLEE accurately estimate relative poses and achieve a high tracking accuracy. In summary, we have shown that we are able to accurately track dynamic objects in realistic scenarios with odometry drift using our algorithm, MOTLEE.